for MIT, and we're working on the grading of the Singapore quizzes. So far, things look pretty good, actually, even though some problems, like problem 5, were a virtual wipeout with just a few people scoring well on that problem. But that was a hard problem. So things are pretty good, and we will hand that out on in recitation on Friday here at MIT and early next week in Singapore. So I thought overall that things look pretty good. We haven't compiled the final, the quiz scores and computed a histogram and so forth. But, from my take on the many hours of our grading session over the last 2 days, I think things look pretty good. So I'm reasonably pleased. I want to remind everybody that we have a programming contest. And this is something that, even if you don't choose to do it in a team, doing it alone probably takes, you can probably end up with a competitive entry within an evening. Okay, because it's really, there's enough stuff there to optimize that it really shouldn't take you long to do pretty well on it. Using a lot of the ideas of how to get performance out of codes using techniques that we've learned in class. So people who are interested in having a little fun at the end of the term because they have nothing better to do on their hands or whatever, let me encourage you to enter. Also, let me encourage you to enter even if you're not going to submit a final solution. If you want to keep track of what's going on and think you might have an evening, I think it's a good idea to register, and then you can decide whether you actually submit a final problem. I want to also, we'll have a handout on this and some email. The final examination room has been changed. It won't be 10-250 because that has no tables, and I think students like tables for doing their exams. Instead, what we're going to do is we're going to break the class into essentially recitations and take the exam in about 5 rooms on the first floor of Building 2. So tell your friends that if they have 10-250 as a location for the final, they are going to be in the wrong place. Okay, so and we'll have a handout and send out information on that. So we're on to the last topic of the course at this point, which is the topic of flow networks. And so this is people just don't know which end of the chalk to use. This is one of these topics which is really fun. We only can scratch the surface of it in this class compared to the huge range of work that has gone on network flows. It's very mathematical, and the algorithms are really a lot of fun because they incorporate lots of data structures, lots of graph theory, and so forth. So let's start out with a definition of what these objects are. So it's just a graph, directed graph, with 2 distinguished vertices. One we call the source, and the other we call the sink. And in addition, it's a edge-weighted graph. So each edge has a non-negative capacity. Okay? So each edge, there's going to be some non-negative capacity. And if some pair UV is not in the edge set, then we define the capacity of UV to be 0. Okay, so for any edge that's not in the set, you can't, it's not going to have any capacity. So let me give you an example. This is going to be a running example. There it is. This is going to be my S for this little example, and T. Okay, and they each have a capacity. This is going to have capacity 3, 1, 2, 3, 1, 3, 2, 3, 2, 3, and 2. Okay, so just a directed graph, but we have with edge weight, but we have now a source and a sink. Okay, so we're going to define a positive flow on G is a function P mapping V cross V into R, satisfying two constraints. The first we call a capacity constraint. And that says that the flow that we have on any edge must be less than the capacity of the edge. Okay, it says that we're going to assign a new function. So we have an edge weight function given, and essentially we're giving another edge weight function. That's what we're going to compute, which is a flow. And it must satisfy the property that the flow is less than or equal to the capacity everywhere, and it also is non-negative. Okay, it can't have a negative positive flow. And the other one is flow conservation. And this says for all U that are not either the source or the sink, says that whatever comes out of U, if I add up all the flow coming out of any vertex U, that's equal to all the flow that's going into U. Or if I subtract them, it's 0. Okay, so who's seen this equation in another course? What course? Okay, but in the context of network flow. Yeah, who's seen this in a non-network flow context? This constraint. Yeah, maybe 6002. What was it called there? There you go. Right. Kirchhoff's current law. Okay, this is Kirchhoff's current law. Okay, which basically says that the current going into any node must equal the current going out. Otherwise, it's not current. So that current is an example of a flow. Okay, so whatever goes in must come out. Okay, so we can, let me put up a flow on here. And the way I'm going to do that is using a notation where I simply put the amount of flow that is going on this edge. It should be less than or equal to the capacity for each edge. So here I ship 1 unit of flow. Here I'm going to ship no flow, 2 units, 2 units, 1 unit, 1 unit, 2, 2, 1, 1, and 2. Did I get everybody? Okay. And so let's just take a look at some node. Let's take this node to begin with. How much flow am I shipping in? 1 plus 1. How much am I shipping out? 2. So I've satisfied the flow conservation property. Okay? And also notice that all these numbers are less than or equal so that I've satisfied the capacity constraint. Here's another one. Okay, so what's shipped in? 2 plus 2. And what's shipped out? 1 plus 1 plus 2. So whatever goes in must come out. Yeah?
What about S?
So S and T are exempted from this requirement. Okay, only the things that are not the source and the sink have to obey flow conservation. And that's the reason. The reason is because S is going to be the source of our flow. Okay, in other words, that's where we're producing the flow. And T is going to be the sink for the flow, that is where we consume the flow. Okay, but everybody else just transports it. Yeah? Oh, element of minus, yeah. Sorry? Minus. Sorry. Yeah, I know people use that silly slash. I don't believe in that stuff. We had a discussion in the staff meeting about that. They told me I was old-fashioned. That set difference you're supposed to, it's like set difference. Okay. So, and in fact, actually this flow out of the source is what we're going to be interested in. So the value of a positive flow is the net flow out of the source. So it is just simply summation over V in V of P of SB minus summation of V element of V of P of VS. Okay, that's the value of the flow. It's how much can we ship out of the source. So for example here, okay, the net flow out of the source here is what? For this example. Yeah. 3. Right? We shipped 1 this way, 2 this way, and we're shipping nothing in. Okay? So flow conservation everywhere, but not on the source and not on the sink. And so the maximum flow problem, which is the problem we're going to look at today and next time, is the simplest of the flow problems. Is find a flow of maximum value. Okay, what's the biggest amount of flow that I can ship from the source through the networks to T? So is this the largest I can ship? Is it possible to ship any more flow than what I've shipped here? Or is 3 the best we can do? The 1, 1. So this one?
Yeah, those two. If you take those 0.
Don't make this 0, you're saying?
Yeah, make the one going up 0.
And the line going up 0.
Yeah, and then you can feed that 1 unit of flow from the bottom right node into the sink.
The bottom right node. The bottom right node. So how about A, B, C, D? Okay. I get one more from D to the sink if but I've got to make sure I have flow conservation at every node, right? Got to make sure what goes in comes out.
Yeah. So you make the 2, 3 a 1, 3. You make the 1, 1 a 0, 1. You make the 1, 3 a 0, 3. And then you shift the D to 2, 2, the D to T.
So you're saying, so let's start. I've got to ship more out of the source. So why don't we say what I start? So you're going to make this be 2, 3? Okay, this is going to be 2, 3. So I have an extra unit of flow here. Okay, so where am I going to take away a unit of flow? So you're going to make this be 0. Okay, so you're saying make this be 2. Make this be 0. Okay, this guy's okay now. Now this guy has one too much unit of flow going in, right? So we're going to take. So now we're going to go from here to here. Why not? From B, I don't think B has to be involved. Since I shipped one less unit of flow here, yeah, let me just send it along here and along there. Okay? Simpler, right? That becomes 3, and that becomes 2. And now I've shipped 4 units of flow. Okay, yeah, there are other ways of getting 4 units of flow shipped through here. Okay? Okay, who will go for 5? Okay, well, it's not going to be shipped this way. There's no point in shipping it here. So I might as well ship it along here. But now I'm sort of stuck, right? So it sort of doesn't look like you can do 5. You can't do 5. This is the maximum flow. So the maximum flow for this is 5. And let me just, so that we have this as a running example for maximum flow, just replace these so that because this is going to get to be a messy diagram by the end. Okay? So that's a maximum flow. Now, before we get to the maximum flow problem, to solving it and understanding what's going on in a maximum flow, I want to observe some things generally about flow networks that are going to simplify our thinking and simplify our notation. So the first thing I want to talk about is flow cancellation. Okay. And basically what flow cancellation says is that without loss of generality, positive flow goes either from U to V or V to U, but not both. Okay? And the reason is because, so let's take an example where I have that, say between B and D here. Okay? So if I have, here I have flow going this way and flow going that way. And the point that flow cancellation makes is it's just as good for me, instead of sending 2 units this way and 1 unit that way, let me send 0 units this way and only 1 unit that way. Okay, and if I do that, the conservation requirements here will still be met, because the net flow entering versus leaving will be the same. Same thing here. And since I'm only reducing the amount of flow that I'll be shipping, the capacity constraint will also be met. Okay, so let me just illustrate that here. So this is sort of true in general for some 2 vertices V and U with these values. That if I have something like 2, 3, as we do over there for B and D, and 1, 2, I can always transform that to a situation where I've shipped flow in only one direction and no flow in the other. Okay. Okay, and the net flow in this case, if you notice, the net flow from U to V in both cases is 1. And so the flow conservation will still be met. Okay, and in particular, you know, always the capacity constraint and flow conservation are still satisfied by this transformation. Okay, so I can always do that kind of transformation on a graph. So here, for example, we'll just ship 1 unit of flow up this way and no units of flow the other way. Okay? And here we already satisfy that constraint. Okay? So that's the simplification. Now, one thing in thinking about it and why can we play this kind of game is there's a tendency of people to think intuitively to think about flow as a quantity, like I'm shipping some number of some product from one place to another, and that's not the right way to think about it. Okay, you want to view flow as a rate. In other words, I'm shipping so much of this product per day. Okay, see, if you have to ship it per day, then it doesn't matter that these warehouses, or whatever you want to think of them as, it doesn't matter that these warehouses might store something, because on average, if you're not going to blow out the storage here, okay, whatever comes in has got to go out. Okay, so you want to think about it as a rate. How much are you doing per day? And then you'll start to see get more of the intuition for what's going on, why it is that things are additive, that what goes in must come out, and so forth. So think about it as a rate Don't think about it as a quantity, and your intuition will help you a lot more. Now, since flow without loss of generality only goes in one direction, there's a notational simplification that we're going to use. And we're not going to see much of positive flow except when we draw it on the diagrams like this. But pretty much our mathematics is going to be based on the notion of net flow. This is just a notational simplification. It also helps to warm you up to some of the issues in network flow. So I'm going to do a new definition. Oh, I shouldn't have erased this, because that's what I wanted to compare it with. Okay. However, so a net flow on G is a function F mapping V cross V into R. So far it looks very similar, satisfying capacity constraint. Okay, so how does this differ from the capacity constraint for positive flow? Check your notes. How does this differ from the capacity constraint for positive flow? Yeah. Yeah, it could be negative. Okay? For the positive flow, we insisted that the flow value P of uv be non-negative. Now it could be negative. Okay? Flow conservation is that the summation of V in V of F of uv is equal to 0 for all u in V minus st. Okay? So the difference here is what compared to what we had before? What did we have before for the conservation constraint? Yeah, it's a difference of summations. We have only one summation, not two. Okay, and that's actually going to simplify our math a lot, to have one summation. So wow, this seems really bizarre. Okay, so there's a third constraint now, and that's what we pay, which is called skew symmetry, which makes this all understandable, which says that F of uv is equal to minus F of VU for all U and V element of V. Okay, this says the flow I ship in one direction is equal to the minus of the flow that's shipped in the other direction. That's why it's net flow. So what we're saying is when I look at the flow for a given node, okay, between two vertices from S to C here, for example, okay, what I'm saying is, well, in this direction, F is going to have the value of 2. Okay, F of SC is the value 2. But if I look at the flow from C to S, I'm going to say that the net flow is minus 2. Okay? So what I'm doing is I'm saying the arrow essentially says what the direction of plus is, the arrow on the edge. Okay, and if I go in the reverse direction, then that's the net flow is minus. And that's why when I take things like the flow conservation constraint, what I'm essentially doing is adding up everything, all the arrows that come in, times the sign of whether it's in or out. Okay, whether it's minus if it's going in and it's plus if it's going out. And that's why this is essentially equivalent to the definition with sums. Oh, it's up there. I didn't erase it. Good. There it is. Good. Okay. So people follow this sort of? So these two definitions are equivalent. So let's prove that as a theorem. Okay, so for the first definition implies the second. Can somebody tell me, if I have a positive flow, what is the net flow between two nodes? How do I define f of uv in terms of the p values that would be on a network? What's the net flow between two nodes? Yeah. P of uv minus p of vu. Okay? So the idea is we take the flow that's in the forward direction and subtract the flow in the negative direction. So you can see directly here the effect of flow cancellation. Okay? Because flow going off in one direction can be canceled with flow coming in the other. Okay? And now, why, if I have this definition, are all of these satisfied? Well, let's just go through them. Is the value of the flow less than or equal to C of uv? Well, yes, because if P of uv is less than C of uv, and this is positive, the constraint continues to hold. Okay, so we have this one. Okay, what about flow conservation? Okay, well, if I sum this, okay, well, that I can replace by the two summations, and I get that summation. Sorry, the other way around. If I have that summation is equal to 0, then when I sum it up, I get that this one is equal to 0. Okay? And skew symmetry, well, if I take the minus of this, that just flips around. It's the minus of this. Okay? So those are equivalent definitions. So if I have a positive flow, I have a net flow. Now let's do the other direction. Okay? How do I define P of uv if I'm given a net flow? So it's actually going to be two cases. So if I give you a net flow between two things, I give you an F, how do I figure out what the P is?
If F is negative, then P is 0 by the capacity constraint. And if F is positive, then we have, since flow cancellation applies,
So you're saying this. Okay, so this is basically P of uv says what's on each of the edges. And the answer is, well, it's just going to be f of uv if that's the direction of the flow. Okay, and 0 on the edge going in the opposite direction. Okay, and so now we can take a look and say, well, if I've satisfied the capacity constraint with f, do I satisfy the capacity constraint under this definition? The answer is yes. Everything is going to continue to be less than or equal to c of uv, and it's also greater than or equal to 0. Okay, so we satisfy the capacity constraint. Does we satisfy flow conservation? Well, once again, yes. If this is equal to 0, then I can split the summation into those things going in versus going out, and I get that equation there. Okay, and that's all I have to show. Okay, so these are two equivalent definitions. We're going to use, for the most part, we're going to use the definition of network flow, so of net flow. Okay, but we are going to continue to draw things with positive flow. And so it's up to you folks to remember that when you see an edge from here to here, you understand that the net flow from D to C is -3. Okay, the positive flow from D to C is 0. Okay, but the net flow is -3. Okay, everybody got that? Okay, a little bit confusing, but I think if you play with it a little bit, you'll see that that this is going to be a nice simplification. So what is then the value of the flow? So that's the end of this proof. Okay. Okay, so the value of the flow, which we denote with vertical bars, okay, is the net flow out of the source. So that I can write just as summation of V in V of F of SV. The flow out of the source. Okay? And that's exactly equivalent to this. Okay, because if I just combine these summations, I basically get the F. Okay, just using this transformation that we have from going from P to F. Okay? And now we're going to use a notation which is going to make this even easy to write and harder to understand until you get used to it, which is instead of always having to write these summations all over the place, when we use a set in an arithmetic formula, we mean a sum over that set. So we write f of s comma capital V to mean the sum of V in capital V of f of SV. So this is an implicit summation notation. Okay, so people understand this notation? How would I write the conservation constraint in implicit summation notation? Yeah. F of this is actually F of for the same constraint for all u. Okay, because all we're doing is taking the sum over V and V. Okay, so Just say this just means the sum of v and v is equal to 0. Okay? So just another way of writing the... what's the flow, the net flow of a node to itself? What's f of vv for little v? Okay, you can actually derive it from this. Yeah. Right, because fu equals minus f of vu. So if this is the same, it says that f of vv equals minus f of vv. Okay, so the only value that can satisfy that is 0. That's the only number which is minus itself. Okay, good. Okay, so let's prove some properties of flow. Let's see, I think I'll leave that. I think we'll go up to this point. Don't need the positive flow definitions anymore. We'll start out with some lemmas that are nicely stated in using implicit summation. For any set x, f of xx equals 0. Now, why is that? So this has got a summation. This means the summation over any v and x of, sorry, this is double summation. This is the summation over u in x of the summation of v in x of f of uv. Doesn't mean that it's the summation of f of vv. Okay? And why is that 0? Yeah?
The inner sum are 0, and the sum of x can be 0.
But the inner sum isn't always 0.
The sum in flow conservation?
The sum in flow conservation, well, that's only if v isn't in there, but u might be.
Yeah, but it's going into t. So that's 0 too.
Yeah, there's actually a little bit more direct way to say what's going on here. What's going on here? New hands, new hands. Yeah. Yeah, skew symmetry, and how does that apply here? Yes, well, so it's more that for anything that's here, okay, if u and v are the same vertex, well, it's 0. We just argued that. If u and v are different vertices, I have both in the summation f of uv and an f of vu. And those two things are going to cancel. Okay? Because of skew symmetry. So wherever I have f of uv added in, I'm also going to be adding an f of vu. Okay? So if I take the flow from a particular subset of nodes, any subset of nodes, to itself, and I look at all the possible flows. So for example, no matter what set of nodes I pick here, let's say I pick C and D, okay, as the two nodes, because that's particularly easy. Let's take 3. Let's say B, C, and D. Then whenever I add in the flow from C to D, I'm also adding in the flow from D to C. So it cancels. Okay? So the net flow is 0 from that, and the same with all the other pairwise things. And so you'll end up with 0. Doesn't matter whether you have S included or not. because you're including it in one direction and then you're canceling it out in the other direction. So net flow is a little bit tricky to think about. In fact, a lot of flow algorithms are, big hairy summations which are 0 all over the place. You just push the zeros around. And the symbols are all, and it's all 0, okay? So a lot of zero sums, okay? Here's another, how about f of x comma y is equal to minus f of y comma x? Why is that true? So if I have two sets now, the net flow from one set to the other set is equal to the net flow of the other set minus the net flow of the other set to the one set. Okay? Well, it's the same reason, skew symmetry, right? It doesn't matter that x and y might have overlapping elements. Okay? And in fact, from this, you could derive that. Yeah? What do you mean by transitivity in this case? F of x comma y plus f of... No. No, but there's something else that does. Okay? And that's the third one. F of x union y, z, is equal to f of x comma y plus f of y comma z if, so I need a constraint here. So the union of two sets I can break into the flow of one plus the flow of the other. Excuse me, this should be x comma z. No, sorry, this is x comma, I got this wrong, this is x comma z. Is there a bug there too? So what's the requirement for that to hold? Right, that x and y have no elements in common. Okay? Because then I can just split the summations. This is just splitting a summation over the index of the summation. So that index is over the elements in y and in x and y. If they have no elements in common, I can just split them into two pieces and just rewrite it. Okay? So I'm not going to go through detailed proofs for these, but you should understand these because we're going to be using, so here we're sort of at a meta level because we've got all these summations going on, but we're not writing summations. But you've got to think of them as summations and make sure that you can mechanically manipulate them. Now let's prove a theorem which some of you will say is obvious, okay? And that is, should be obvious, but of course the proof is a little more involved using this notation. It says the value of the flow is the net value of the flow into the sink. If we define the value of the flow as the value out of the source. And flow conservation says, well, nobody can accumulate it, so where must it all end? In the sink. Okay, and in fact, if we look at this, we shipped 4 units out of S, and we have 4 units going into T. Right? Okay, didn't get caught up anywhere. Anything that went in had to come out of all those other nodes. Okay, so this should be obvious. Let's prove this using the implicit summation notation, give you a little more practice. So F is defined to be F of S comma V, net flow out of the sink, out of the source. Okay? So that's equal to F of VV minus F of V minus S, and here I'm cheating a little because I'm also, this is little s, I'm also now removing set braces. So I'm really being sloppy. You know me, I love to be sloppy with notation, as long as I know what I'm doing. But I love to be, I hate writing all kinds of crazy symbols I don't have to. I like to be succinct and direct and short and so forth, comma v. So we're omitting set braces there, which we probably shouldn't, but you know, I know what I mean. Okay, why is this true? Yeah. By the third, right, by this third line of this lemma. Okay? Because v, so I have basically, this is saying f of sv plus f of v minus sv is equal to f of vv. And that's basically what this says. Here vv is this, and one of the sets is v minus s, and the other set is just the set containing s. Okay? So basically it says I can split those summations. Okay, looking at the net flow from the net flow of the whole set to itself minus the flow out of the source. Okay? Excuse me, minus the flow of everything except the source. Okay? So this, we know, is what? 0. So this whole thing is equal to f of just v comma v minus s. Why is that? Skew symmetry. Okay, that's basically, this is skew symmetry generalized to sets. Okay, and that's basically what we've got here. Okay, and then I say this is equal to f of v comma t plus f of v comma v minus s minus t. And why is this true? Yeah. Excuse me? I think this is right. Okay. Why is this? Yeah? Yeah, lemma 3 again. Okay, we're splitting the summation. Okay, we're splitting the summation. Okay, we're saying that if I take this set plus this set, it's equal to that set. It's actually lemma 3, but with these two roles reversed. But I can prove that from this if I go through 2 steps of skew symmetry, if I don't want to prove it directly. Okay, so basically it's lemma 3 again. Okay, and that's equal to what? I say that's equal to f of v comma t. I.e., this is 0. Why is this 0? Yeah, flow conservation. Okay, because every element that I can pick for u here, this is going to be 0. Okay, there's a double summation going on here. Okay, and for every element of 1, it's basically 0 because of flow conservation. So we're done. Okay. Okay, so on the final, be prepared to manipulate implicit summations. Okay? Okay. How are we doing on time? Got to move. Okay. Cuts. cut ST is a partition of V. What does that? What do I mean by a partition of V? What does that mean? When I say ST is a partition of V. Yeah.
V is split up into two undisjoint subsets, S and T, such that S union.
Right. Or another way of saying it is that T is equal to V minus S. Okay, T contains everything in V that is not in S. And of course, I could once again use that silly slanty thing. Okay, that doesn't look to me look like a minus is the problem. I like it when it looks like a minus. Such that, so this is different from a cut. We saw cuts for which other type of algorithm did we look at where we talked about cuts? Minimum spanning tree, right. We used cuts. Now there we use general cuts. Here, a cut of a flow network has the additional property that it also separates S into one set and T into the other. Okay, so it's got to be something where S is in one set and T is in the other. Okay, and if F is a flow, the flow across the cut is f of s comma t. So let's take a look at what that means on this flow network. Okay. So for example, suppose that this is an S and this is an S. So those guys are in S and the others are in T. Okay, what is the flow across the cut ST? What's f of ST here? Four. Good. Why is it 4? Yeah, because net flow out of B is 0. Good. Okay, and everything it's going to is in T, right? So that's all we care about. And here, everything here is going to T as well. I probably should have picked an example where, what if I make this be the cut? Now what's the net flow? A little bit more complicated. It's the same thing? Is it still 4? Why is it still 4? No, it's still 4. He's right. What if I added this node in? Still 4. We're going to prove that in a little bit. Okay? We're going to prove that in a little bit. Okay? In fact, we're going to prove that right now. That's a lemma. The value of the flow is f of st for any cut st. As long as I have S on one side and T on the other, if you think about it, the net flow, it's either going to flow in or flow back or whatever, but the net flow is going to be f of st. So here's a proof. So f of st, we know, is just f of sv minus f of ss. So why is this one? Yeah, it's the splitting of summations lemma. Okay, step 3. So that's just equal to f of sv, because that's 0. Okay, and so that's equal to f of s comma v plus f of s minus little s comma v. So what is this? Why is this true? So I've basically taken s and I've split it into 2 pieces. So that's once again splitting the summation. Okay? And now this is equal to what? F of s comma v, because this is 0. Why is this 0? Why is that 0? Dun, 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 dun. That's 0. Yeah. Flow conservation. Because for every element here, this is not in, this is a set which is neither, for every u that I could pick out of s minus s, it's not in, it's, s isn't in here, and t isn't in here. Little s and little t are not in here. So for every one of those, f of u comma v is 0. So the summing of them is all 0. As I say, a lot of these things are just shifting the zeros around. Okay? And that's equal to what? What's f of s comma v? By definition. Yeah. Well, what are we trying to prove? Yeah, it's the value of f. What are you trying to prove? That's by definition. Okay? Okay? So any cut, the value of the flow across any cut is S of uv. And so it's no surprise that although we could add up all these numbers, you don't have to do that. Ooh, I just thought of a good final question. Okay. Okay. Now, you guys know this lemma? So in fact, notice that this theorem is in fact a corollary of this lemma. Because what are the sets here that I take? This theorem is a corollary of that lemma. Two-line proof. Yeah, so basically, here, okay, I can take a cut that separates t from everything. Make this be s. And here's t. Let me look at the flow across the cut. It's got to be the same. Okay, and then that gives me the same thing and with just one line of manipulation to cancel the zeros out of that. Okay? So that's a powerful theorem. Okay. The capacity of a cut ST is just C of ST. Okay? So let's make this a little bit easier by making this go back to the original. Okay, what's the capacity of this cut? Yeah, I got to do some addition here because it's double-digit answer. At least I think it's a double-digit answer. Yeah. 15. That's not what I got.
Just add up all the capacities of this adjacent, or if you subtract off
What'd you get? 11. That's right. Let's just see. Okay. So what you did is actually very common, and we'll talk about that. So if I add up the capacities of S going to things that are not in S, essentially, then I add up 3 plus 2, but I don't add up anything having to do with this, just the edges going out. So that's 3 plus 2 for the capacity going out. There's no skew symmetry or anything with capacities. Capacities are just capacities. Okay, so there's no magic that happens with capacities. Okay, so that's 3 plus 2 is 5. And from here, I have to add in 1 for that one, 2 for that one, and 3 for that one. That's another 6. So that's 11. Okay? The edges going in, ignore them. Okay, they have no bearing on what we care about for this. Okay, no bearing whatsoever. Okay? So the capacity is just capacity of ST, and that's the one trickiness about this is you can get your head so full of flow that you start computing capacities as if they're flow and they're not. Okay, capacities have a direction, and they have a quantity, and you just take the edges that are going from one set to the other in order to compute the capacity. It's how much for something that's in the set to something that's not in the set. Okay, you don't have any of the other advantages you do in things. Okay, so the proof of this is pretty straightforward because all you're doing, oh, sorry, I've got to give a corollary. Corollary to that lemma. Okay. The value of any flow is bounded above by the capacity of any cut. Okay, so I take a look at any cut. So here, this cut has capacity 11, and notice the flow value is less than or equal to it. Okay, so any cut that I take, the flow value has got to be less than that, less than or equal to that. Okay, and why is that true? Why is this a pretty easy corollary? Okay, so the value of any flow, well, we know the value of any flow is just f of st. Right? And I claim that this is true. Why is that true? Yeah. Yeah, by the capacity constraint. Just go one by one through each of these. Okay? Just go one by one through each of these. Okay, when I do the summations, if I blow out the summations here. Okay? And whenever you're confused about the implicit summation notation, let me encourage you to write out the summation. And then what you'll do is you'll start doing that in your head, and you'll start to have some facility for seeing the implicit summation or not. Okay? So on the flow network here, once again, notice that this is going to be true, okay, that for every edge that we care about, okay, the flow is less than the value that's going out, and then we're subtracting some stuff, potentially, right? But we're not adding that into, the upper bound of the capacity there is just 0. Okay? Okay. Now some really good stuff. This is all in preparation. All the algorithms come next time. Okay? We're just gearing up for this stuff. Let's see. So we've got cuts. We've got, I think that we can erase finally our example here. I hope so. Okay. Residual networks. So I would highly recommend, by the way, that people review what we've done today before coming to lecture on Monday, where we're going to continue this. In other words, before class or Sunday or whatever, just spend a few minutes going over and reviewing the lecture notes for this lecture, just to get refreshed, et cetera, because we're going to launch right in as if the lectures were, this is sort of a one lecture in 2 lecture sessions. Okay, so we're really going to just launch into the next one. So residual network. So all these definitions I'm going to want you to be comfortable with. Let F be a flow on G equals VE. Then the residual network actually, I could have left that one up. Okay. G sub F of V comma E sub F. So it's a network G sub F, which has the same vertex set as G, but it has a new edge set, E sub F. Okay. Is the graph with strictly positive residual capacities C sub F of UV, which is defined to be C of UV minus F of UV. And this is greater than 0, for those for which it's greater than 0. Okay, strictly positive residual capacities. Okay? So what this is saying is if I've got a capacity of UV, okay, and I've already pushed F of UV units of flow on that edge, then the residual capacity, what's the capacity of how much more flow I can push? Okay, in other words, here I can push this amount more flow, and then this edge will be saturated. The edge UV will be saturated. Okay, so edges in E sub F admit more flow. So for example, suppose I have G and I have a couple of nodes in it, U and V, say, U and V, and I've shipped 0 out of 1 unit there and 3 out of 5 units there. Then in G sub F, I'll have U and V. And what will be my capacities in U and V? So how much will I in particular have from V to U, for example? 2. because I can ship 2 more units from V to U. And what will I have from U to V? It's not 1. So you're thinking of positive flow rather than net flow. Remember, we draw positive flow, but we think net flow. So how many more units can I ship from U to V? Or units per second, or whatever, because you want to think of flow as a rate. So I can certainly ship 1 unit along this edge, but how many can I ship backwards along that edge? I can ship, no, I can ship 4. Okay? So let's just do the formula here. What is the net flow from U to V? What's the net flow from U to V? Minus 3 is the net flow from U to V. I take the capacity, which is 5, and I subtract the net flow. So that gives me the 2 here. Here I take the capacity, it's 1. Excuse me, I take the capacity here, it's 1. Okay, and I subtract minus 3, that gives me 4. Okay, because I'm doing net flow here, not positive flow. And the interpretation of that is, rather than shipping, if I'm saying how much more could I ship in this direction, okay, well, I could stop shipping the 3 I'm shipping, and I could ship an additional 1. Okay? So residual graph, you've got to remember, this is net flow. So don't get confused between positive flow and net flow. Okay, and in particular for residual graphs. So everybody understand how I came up with the residual graph here? This tells me now how much more I can ship from one direction to the other. Now, it's going to be important for the performance of our algorithms that I know how big the residual graph is in terms of number of edges. Okay? So how big is this at most? Somebody give me a bound. Yeah. No, it could be bigger than E. 2E. Good. Because I might not have an edge in each direction, but in the residual graph, I might have an edge in each direction. Okay, so for example, if I have a graph like this, where I ship 1 unit, there's no edge this direction, and I ship a unit of flow there, well, now I can ship a unit of flow back. And so I'll end up in the residual graph having to add in that edge, but just pairs. Okay? Okay, let's see. So the last concept is the concept of an augmenting path. Any path from S to T in G sub F is an augmenting path in G with respect to F. Okay? And the flow value can be increased along the augmenting path by C sub f of p, which is equal to the minimum over all edges in the path of the capacity, the residual capacity of that edge. Let me give you an example of this. So suppose that G is this graph. S and T. And this is just one path in the graph. Okay, and suppose we've shipped 3 units out of 5 on here, 2 out of 6 here, 0 out of 2 here, 5 out of 5 here, 2 out of 3 here, and 2 out of 4 here. So that's my original. This is just one path. Now, notice that this path is not path in a normal graph sense because it's going backwards along this edge. Okay? And in particular, it's also going backwards along this edge if I look at the flow. And so G sub f is so I can ship 2 more units this way, or I can ship 3 more back that way. Okay? Here I can ship 4 more in this direction, or I can ship 2 back. Here I can ship 5 back in this direction, and in this direction, 0. So that edge doesn't exist, actually. Did I do this right? No, I can ship a total of 7. Got that wrong. 7 in this direction. Because I can ship 5 back, plus I have an extra 2. Okay? Here I can ship, in this direction I can ship 2, and in this direction I can ship an additional 1, and here I can ship 2, and in that direction I can also ship 2. Okay? And so for this, C sub f of p is equal to, so notice this is a path in G sub f here, okay, taking just the top edges here. And the minimum along this path is 2. And so the idea here is that if I have an augmenting path, what I can do is I can ship 2 more units of flow along here in this original graph, okay? And if I have to go backwards on this, I simply reduce the flow that's already shipped there. Don't ship it this direction, okay? And notice that that will preserve all the flow conservation constraints, okay? And it will increase the flow because the amount I've shipped out of S or into T is now increased. And that's the basis for most of the algorithms on network flow, not all of them. But a very important one is this idea of using augmenting paths. So next time, we're going to do the max flow min-cut theorem, okay, which is going to pull all of this together. That's how we start out, showing that the maximum flow in a network is the same as the capacity of the minimum cut that you can make in the network. And then we're going to look at algorithms for actually solving that, which are very, very, if you thought shortest paths were fun, okay, these are going to be even more fun. And if you didn't think shortest paths are fun, well, such is life.